So before we get started with this problem, we need to define a few terms and explain them before we can start. So first, back work ratio is the ratio of the compressor work to turbine work, which is RBW. And the pressure ratio is defined as RP, and it's P2 over P1. We also need to understand what effectiveness means, and it is the extent to which a regenerator approaches an ideal generator. We'll look at effectiveness in their percentages in a little bit. So the Brayton cycle, along with the Otto, Diesel, Stirling, and Ericsson cycles, all use standard air assumptions. And these assumptions are that T1 equals 300 Kelvin, P equals 100 Kelvin. We have constant specific heats. Air circulates in a closed loop as an ideal gas. We are internally reversible. Combustion process is replaced by heat addition, and exhaust process is replaced by heat rejection. Not all of them will be used in this problem, but oftentimes you'll need them. So regeneration in the Brayton cycle, it's when the high pressure air leaving the compressor can be heated by transferring heat from it to the hot exhaust coming from a turbine via the heat exchanger or the regenerator. We can use multi-stage compression with intercooling and multi-stage expansion with reheating for these processes. These change the work required to expand and compress gases. With the addition of regeneration, reheating, and intercooling, there becomes a lot more states to deal with because of everything going on within the system. So with that, we can start our problem. So consider an ideal gas turbine cycle with 2 stages of compression and 2 stages of expansion. The pressure ratio across each stage of compression and turbine is 3. The air enters each stage of compression at 300 Kelvin and each stage of the turbine at 1200 Kelvin. Determine the back work ratio and the thermal efficiency, assuming A, no regenerator is used, and B, a regenerator with 75% effectiveness is used. So we can start by writing our knowns and our unknowns. So our knowns, we are an ideal gas. The pressure ratio is 3. The T compressor in is 300 Kelvin. The T turbine in is 1200 Kelvin. And then for our unknowns, we need to find the back work ratio for no regenerator, the back work ratio with the regenerator, and that's 75%. Then we need to find the thermal efficiency with no regenerator and the thermal efficiency with the regenerator. So our assumptions, like I said, we're an ideal gas, and we have our air standard assumptions. So up here I said 300, but it should be 400, like the problem said. And remember, we just talked about our air standard assumptions in the beginning of the video. So now we can look at our diagram that we can draw. Actually, first I'll show you 2 examples. So this diagram right here, you can see has less steps than this one. Label them 1 and 2. And 2, it's similar to the problem we're doing now, where there's 2 stages of compression and expansion. These are 2 stages right here, and these are 2 stages right here. You can tell because of the isentropic processes going on and how on the bottom and top there's 2 isothermal processes going on. as in the first diagram, there's not really much going on. There's a lot less steps in the problem. So our diagram in this video is pretty similar to the one I just showed you. The steps are drawn out a little differently, but we can say that T5 equals T7, T6 equals T8, and we can see that right here. And then down here, T4 equals T2, and T3 equals T1. Now with all of these, it's the same with the H values. So we need to keep that in mind as we're finding values for our problem. All right, so we're trying to find the back work and efficiencies. So we need to start by getting all of our H values and pressure ratios from table A7, because to find back work, you need the work which comes from our H values. And we're using table A7 just because that's the air tables. So now we're gonna go back up. And we know we're at 400 degrees. So all of our values are gonna come from right here to begin with. So first, at 400 degrees Kelvin, T3 equals T1, and remember that's the same for our H values. So our H value off the table I just showed you, it's going to be 400.98 kilojoules per kilogram, and that's going to equal H3 as well. And then the pressure ratio from that table is 3.806. Now using our pressure equation, we can find PR2 from P2 for P1 times our pressure 1, which we just found from the table. And the P2 over P1, like I said in the beginning, is our pressure ratio. So it's this RP, and that's 3. So we're going to say 3 times 3.806, which gives us 11.418 as our PR2. So next we need our H2 value. And to get that, we're going to go down here to these values, and we need to interpolate. So the reason we're going to these values is because we just solved and got 11.418, and that's right in between these two values. So we're going to use this set of data right here. All right, so we can say that H2 equals 544.35 plus 554.74 minus 544.35, and then times 11.418 minus 11.10 over 11.86 minus 11.10. And then this should give us an H2 value of 548.697 kilojoules per kilogram, which equals H4, and remember that's because of the graph. So finding our next set of values, because we're switching temperatures, we just found these H values down here, and now we need to find them up here. So we're going to be switching temperatures, so we can say at 1200 degrees Kelvin, this is T5 equals T7, so our TH and our H5 and H7 values are going to be the same. we have H5 equals 120 or 1277.79 kilojoules per kilogram, and PR5 equals 238. And now just to show you on the table where these are at, it's just the other side of the table since we're using a larger value, but we're getting these from this 1200 right here. And we're using, this is our PR, this is our H. All right, going back over, we have these two values. So now we're going to solve for PR6. So we can say PR6 equals P6 over P5 PR5. So that's going to be 1/3. That's our pressure ratio, but flipped now that we're in a different section of the graph. 232, because that was PR5. And then we're going to get a PR6 of 73.33, repeating. So now we're going to need to interpolate again to find our H6 value. And remember, H6 is the same as H8. So H6 equals H8 equals 932.93 plus 955.38 minus 932.93 times 79.33 minus 75.29 over 82.05 minus 75.29. And that gives us H value, H6 equals H8 of 946.35. And if you forgot where we found those, they're over here on this side of the table. All right, so now that we have interpolated and found these, we can finally solve for our backwork ratio. When you're doing these problems, I highly recommend keeping a separate space just to write down all of your values because they do get confusing sometimes. So for our first part, with the no regeneration, we can say the backwork ratio equals Wn compression over W out turbine. And that's the exact same formula that I explained in the beginning of the video. So this equals 2 times H2 minus H1 over 2H5 minus H6. And we put a 2 out there just because there's 2 turbines and 2 compressors. So this is 2 times 548.697 minus 400.98 over 2 times 1277.79 minus 946.35. And remember, throughout this video, all the H values are kilojoules per Kelvin, but it looks a little neater if you just don't write that. So the backwork ratio then equals 0.4457 or 44.57%. And the backwork ratio doesn't vary depending on if you have a regenerator or not. So this is the same backwork ratio for both parts of the problem. So we just solved half the problem so far. So we can say for regenerator and no regenerator. All right, so based off this, we need to find the efficiency. And our efficiency equation is N equals W net over heat in, which is then equal to W out turbine minus W in compressor over H5 minus H4 plus H7 minus H6. And we know all these values because we have the table, and it's really easy to kind of look at them and visualize when you have the table like that. So then this is going to equal 662.88 minus 295.434. It's easy to get the net work just because from finding the back work ratio, we pretty much have that already. So then we have these, and then 1277.79 minus 548.697, and then plus 1277.79 minus 946.35. All right, so then that's going to give us an efficiency of 0.3465 or 34.65% for no regeneration thermal efficiency. All right, so for the last part of the problem, we need to find the thermal efficiency with 75% effectiveness. So part B, it's going to be the same equation pretty much, but slightly different for the heat. So regen equals W net over Q in, but instead of just Q in, we need to include the regenerator, so it's going to be W net, work net's about the same, and then on the bottom Q in minus the Q regenerator. And if we go back to our graph, we can see where the regeneration is. So we see it's right here on the graph and then right here. So to find the Q regeneration, the heat regeneration, the equation we use is this right here. So Q regen, and then that's our effectiveness. And then H8 minus H4. So that's where our regeneration is. And then our effectiveness is 75, H8 is 946.35 minus 548.697. And remember, this is kilojoules per kilogram. And that gives us a Q regeneration of 298.24. All right, so now we can finally finish our problem. The thermal efficiency for generation is 367.446, and this is the work out minus work in, which is the work net. So we found that in the last part of the problem. And then 1060.533 minus what we just found, 298.24 kilojoules per kilogram, which gives us an efficiency of 0.482 or 48.2%. Alrighty. So again, I think the number one thing to take away from this is there's a lot of parts of the problem, so having a graph like this one really helps to visualize everything and keep track of where your H values are going.